In the cosmic ocean, there are shadows. Not the simple shadows cast by a planet blocking the light of its star, but absolute voids. They are regions of infinite silence, stitched into the very fabric of space and time. They are the universe's ultimate dead ends, gravitational prisons from which nothing, not even light, the fastest thing in existence, can escape. We call them black holes. They are not just objects. They are locations where the known laws of physics surrender, where space becomes a waterfall and time comes to a halt. For centuries, they were a ghost in a machine, a mathematical curiosity. But today, we know they are real. They lurk in the dark, patiently waiting. The story of black holes is the story of humanity's struggle to comprehend the most extreme, the most violent, and the most mysterious phenomena our universe has to offer. The idea of a star so dense that its gravity could trap light is not new. It didn't begin with Einstein, but in the late 18th century, with a British natural philosopher named John Michell, pondering Isaac Newton's laws of gravity and the idea that light was made of particles. Michell reasoned that a star sufficiently massive and compact would have a gravitational pull so strong that its own light could never leave its surface. He called them dark stars. At the same time, independently in France, the brilliant mathematician Pierre-Simon Laplace proposed a similar concept. It was a fascinating, but ultimately philosophical, idea. Without a deeper understanding of light and gravity, it remained a curiosity, a footnote in the history of astronomy. For over a century, the idea lay dormant. Then, in 1915, everything changed. Albert Einstein published his theory of general relativity, completely rewriting our understanding of gravity. In Einstein's universe, gravity wasn't a mysterious force acting at a distance. It was a consequence of mass and energy warping the very fabric of reality, a four-dimensional continuum he called spacetime. Imagine a stretched rubber sheet. A bowling ball placed in the center will create a deep dip, and a marble rolled nearby will circle this dip. Not because the ball is pulling it, but because it is following the curve in the sheet. This is gravity. Stars, planets, and even our own bodies are creating tiny, insignificant curves in spacetime. But Einstein's elegant equations contained a monster. Just months after their publication, a German physicist named Karl Schwarzschild, serving on the Russian front during World War I, found the first exact solution to Einstein's field equations. He described the gravitational field outside a single, spherical, non-rotating mass. His solution was perfect, but it held a terrifying prediction. If you could squeeze enough mass into a small enough space, what we now call the Schwarzschild radius, the curvature of spacetime, would become infinite. It would create a bottomless pit in the fabric of reality, a one-way membrane. Anything that crossed this boundary would be trapped forever. Einstein himself was horrified by this implication. He thought nature would surely have a way to prevent such an absurd object from forming. He believed these singularities were just a mathematical flaw, an impossibility that wouldn't exist in the real universe. He would be proven wrong. The anatomy of a monster. To understand a black hole, we must first understand its anatomy. It isn't a solid object you could stand on. It's a region of spacetime, defined by a series of boundaries. The most famous of these is the event horizon. This is not a physical surface, but an informational one. It is the ultimate point of no return. Once you cross the event horizon, the pull of gravity is so immense that the escape velocity exceeds the speed of light. Since nothing can travel faster than light, escape is impossible. The laws of physics inside the event horizon are warped. Here, The gravitational pull is so strong that all possible paths for any object, any particle, any ray of light, lead in only one direction, inward, toward the center. Space itself is flowing inward faster than light, like a river plunging over a waterfall. To try and escape would be like a salmon trying to swim up a waterfall faster than the water is falling. It cannot be done. From an outside observer's perspective, something truly strange would happen. If you were watching a brave astronaut fall toward a black hole as they approached the event horizon, their light signals would have to fight harder and harder against gravity to reach you. They would appear to slow down, their image becoming redder and dimmer, until they seem to freeze in time at the edge, fading into nothingness over an eternity. For the astronaut, however, time would pass normally as they slipped across the horizon, blissfully unaware, at first, that their fate was sealed. At the very center of the black hole lies the second, and far more mysterious, component, the singularity. According to general relativity, all the mass of the black hole, the equivalent of millions or even billions of our suns, is crushed into a point of zero volume and infinite density. Here, spacetime is infinitely curved. The singularity is the point where our understanding of the universe completely breaks down. The laws of physics as we know them, including Einstein's own theory, cease to function. What is a singularity? Is it a tear in reality, a gateway to another universe, or simply a monument to the limitations of our current theories? We do not know. To truly understand it, we would need a theory that unifies general relativity with quantum mechanics, a theory of quantum gravity, the holy grail of modern physics. There is another famous concept associated with black holes, one born from their extreme gravitational forces. If an object, like a star or an unfortunate astronaut, gets too close, it will experience incredibly powerful tidal forces. The gravitational pull on the part of the object closer to the black hole will be exponentially stronger than the pull on the far side. This differential would stretch the object vertically while squashing it horizontally. It would be pulled apart, atom by atom, into a long, thin stream of matter. This process has the grimly descriptive name spaghettification. How to find a ghost for decades, black holes remained theoretical. The main problem was their very nature. How do you find something that is perfectly black, that emits no light, set against the blackness of space? The answer, paradoxically, is to look not for the black hole itself, but for the chaos it creates in its immediate vicinity. The first evidence came from the heavens in the form of powerful X-rays. When a black hole is part of a binary system with a star, its immense gravity can pull material from its companion. This gas doesn't fall straight in. Instead, it forms a vast, swirling disk of superheated plasma called an accretion disk. As the material in this disk spirals toward the event horizon at nearly the speed of light, friction and magnetic forces heat it to millions of degrees, causing it to glow fiercely, not in visible light, but in high-energy X-rays and gamma rays. This makes the region around a black hole one of the most luminous and violent places in the entire universe. In 1964, astronomers detected an incredibly powerful X-ray source in the constellation Cygnus. Named Cygnus X1, it became the first strong candidate for a black hole. By observing the star it was orbiting, they could calculate the mass of the unseen object. It was too massive to be a regular star or even a dense neutron star. It had to be a black hole. We also find them by watching the stars. At the heart of our own Milky Way galaxy, 26,000 light-years away, lies a supermassive black hole named Sagittarius A*. For decades, astronomers like Andrea Ghez and Reinhard Genzelwerk that would win them the Nobel Prize. Meticulously tracked the orbits of the stars closest to the galactic center. They saw these stars whipping around a central point at incredible speeds, orbiting a region of complete darkness. There was nothing there to see, but by applying Kepler's laws, they could calculate the mass of whatever was gripping these stars, a staggering 4,000,000 times the mass of our Sun, all packed into a space smaller than the orbit of Mercury. The only possible explanation was a supermassive black hole. We are all, right now, orbiting this sleeping giant. But the most profound proof of their existence came not as light, but as a ripple in the fabric of spacetime itself. Einstein's theory predicted that cataclysmic events, like the collision of two black holes, would send out vibrations in spacetime called gravitational waves. For 100 years, this prediction remained unverified. These ripples are infinitesimally small. By the time they reach Earth, they can stretch and squeeze space by less than the width of a proton. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, a pair of incredibly sensitive detectors in the United States, achieved the impossible. They detected the faint chirp of two stellar mass black holes, each about 30 times the mass of the Sun, spiraling into each other and merging in a distant galaxy over 1 billion years ago. For the first time, we did unsee the effects of a black hole. We heard the sound of spacetime ringing from their violent embrace. This era of discovery culminated in the ultimate achievement, a photograph. Taking a picture of a black hole is monumentally difficult. They are relatively small in cosmic terms, and impossibly far away. Sagittarius A*, despite its huge mass, would appear in our sky to be the size of a donut on the surface of the Moon. To see it, you would need a telescope the size of the Earth. So that's precisely what scientists built. The Event Horizon Telescope is not a single telescope, but a global network of radio telescopes, all synchronized by atomic clocks and observing the same target at the same time. By combining their data, they create a virtual telescope with the resolving power of a planet-sized dish. In 2019, they released the first ever direct image of a black hole as silhouette, the supermassive black hole at the center of the galaxy M87, 55 million light-years away. We saw the shadow, the dark central region where light is trapped. Surrounded by the fiery, distorted glow of its accretion disk, the ghost had finally been captured on camera. The frontiers of physics, with their existence confirmed beyond all doubt. Black holes have transformed from theoretical oddities into essential cosmic laboratories. They are the crucibles where our theories of physics are pushed to their breaking points, and where the deepest paradoxes of the universe emerge. One of the most profound ideas came from the late Stephen Hawking. In the 1970s, he combined the principles of general relativity with the strange rules of quantum mechanics and made a startling discovery. Black holes are not entirely black. Due to quantum effects at the edge of the event horizon, they should very, very slowly radiate away energy and particles, a process now known as Hawking radiation. This means that over immense, mind-boggling timescales far longer than the current age of the universe, a black hole can completely evaporate and disappear. This remarkable idea, however, created an even deeper problem, the information paradox. A fundamental law of quantum physics states that information can never be destroyed. The information that makes a book, the specific arrangement of its particles can be scrambled, burned, or torn apart, but in principle, it's never truly gone. Yet, if a book falls into a black hole, it seems to vanish. And if that black hole later evaporates away into a featureless mist of Hawking radiation, where did the information about the book go? Has it been permanently erased from the universe, violating the laws of quantum mechanics? Or is it somehow encoded in the faint radiation, or perhaps stored somewhere else entirely? This is one of the biggest unsolved problems in theoretical physics. It represents a fundamental clash between our two great pillars of understanding: general relativity, which says the information is gone forever behind the event horizon, and quantum mechanics, which insists it must be preserved. This paradox points to the heart of the great unknown. What truly happens inside a black hole? The singularity is a placeholder for our own ignorance. Some theories suggest that the infalling matter doesn't crush down to an infinitely dense point, but instead rebounds in a big bounce, potentially seeding the birth of a new universe. Perhaps black holes are cosmic wormholes, tunnels through spacetime connecting distant parts of our own universe, or even acting as bridges to entirely separate realities. The mathematics allows for these possibilities, but we have no way to verify them. They are the alpha and the omega of the cosmic story. Black holes are born from the death of the most massive stars. Yet, the supermassive black holes at the center of galaxies appear to be essential architects, shaping the very evolution of the galaxies they inhabit. They are destroyers of worlds, yet their accretion disks provide the energy that can trigger new star formation. They are the darkest places in the cosmos, yet they shine with some of the brightest light. They are the simplest objects imaginable, defined by only three properties: mass, spin, and charge, yet they contain the most complex and profound mysteries in all of science. Our quest to understand them forces us to confront the nature of space, time, information, and reality itself. The black hole is a cosmic riddle, and its silhouette, once a figment of theory, is now a beacon on the horizon of human knowledge. It is a locked door, and we have only just begun to knock. But now, we are knocking with instruments of unimaginable power. Humanity is building a new generation of eyes that are fundamentally changing our view of the cosmos. The James Webb Space Telescope, poised in the silent darkness of deep space, was designed to look back in time to the universe's first dawn. With its infrared vision, it can pierce through veils of cosmic dust to witness what has been hidden: the birth pangs of the very first galaxies and the formation of the gargantuan black holes at their cores. Webb's initial data is already painting an unexpected picture, surprisingly mature. Overly massive supermassive black holes existing far earlier in the universe's history than our models predicted. This challenges our understanding of how they could grow so big, so fast. Did they grow slowly from the seeds of dead stars, or were they born directly from the collapse of primordial gas clouds at the dawn of time? It is one of cosmology's greatest chicken and egg conundrums, and the answer could rewrite our story of galaxy formation. Meanwhile, our virtual telescope on Earth, the Event Horizon Telescope, is getting sharper. Scientists are now planning for the INGET, the Next Generation Event Horizon Telescope. This project aims not just to take another picture, but to create a movie by adding more telescopes to the network and observing at higher frequencies. With it, we could watch the real-time motion of superheated plasma swirling around the event horizon. We could directly witness one of the most extreme predictions of Einstein's general relativity: frame dragging, the process by which a spinning black hole literally drags the fabric of spacetime around with it like a vortex. We may even be able to resolve the thin, bright circles of light around the shadow, the photon rings, which are formed by light that has managed to orbit the black hole multiple times. This isn't just an image. It's a precision test of the fundamental physics of a black hole's doorstep. And then there is the language of silence: gravitational waves. The chirps detected by LIGO and its collaborators were the loudest shouts in the universe. But the next generation of detectors, like the space-based laser interferometer space antenna. Or LISA will hear not just the shouts, but the cosmic whispers. They will be sensitive enough to detect the constant, low-frequency background hum generated by slower, less violent mergers, like a smaller black hole orbiting a supermassive one. This will allow us to create a complete census of the black hole population across the cosmos to track how they merge and grow throughout cosmic history. We are beginning to listen to the universe, not just look at it. And we are hearing its deepest secrets in the music of black holes. The missing link, and yet, even with these advanced tools, a great mystery persists. We know of two main families of black holes, the stellar mass black holes, ranging from a few to a few dozen times the mass of our Sun, formed from the collapse of massive stars at the end of their lives. And the supermassive black holes, the behemoths lurking in the centers of galaxies, with millions or even billions of solar masses. But what about the space between? Why does there appear to be a vast desert separating these two populations? Finding this missing link, the so-called intermediate mass black holes, or IMBHs, with masses from a few hundred to a few 100,000 times that of the Sun, is one of the most active hunts in astronomy. Why are they so elusive? Because there is no obvious mechanism to create them. They are too massive to form from the collapse of a single star, yet they aren't the titans we find at the heart of a major galaxy. One theory suggests they are born in the hearts of ancient, dense collections of stars known as globular clusters. In these crowded environments, heavy stars and smaller black holes can sink toward the center, potentially building up a larger, intermediate mass black hole through a series of mergers over cosmic time. Another possibility is that they were the original seeds in the very early universe from which the supermassive black holes later grew. Astronomers are piecing together the evidence. Hints of their existence appear when we see stars strangely accelerated in the core of a globular cluster, or detect an unexpected flare of X-rays from the center of a dwarf galaxy. Sometimes, the sudden, brilliant flare of a tidal disruption event, an unlucky star being spaghettified by an unseen object, can reveal the mass of the monster lurking in the dark. Each potential candidate is another crucial step toward finding the missing member of this cosmic family. Understanding this missing link will fill in the blanks of how the largest black holes came to be and how they, in turn, built the galaxies around them. The fate of information and the nature of reality. As our observations improve, we see more clearly that black holes are not just objects. They are the battleground where our most fundamental principles of physics collide. Hawking's information paradox remains unsolved, pushing theoretical physicists toward radical new ideas about the nature of reality itself. Perhaps the event horizon is a giant holographic surface upon which information is encoded, so that a copy of everything that falls in is preserved. This holographic principle suggests that the three-dimensional universe we experience might actually be a projection of information stored on a more fundamental two-dimensional surface. In this mind-bending view, we are all living on the event horizon of a black hole. Other theories focus on the singularity itself. Perhaps this point of infinite density is not a singularity at all, but a Planck star, an unbelievably small and dense object where the pressure of quantum gravity prevents further collapse. In this scenario, matter that falls into a black hole isn't crushed out of existence, but is added to this exotic object, to be released back into the universe with its information intact when the black hole evaporates. Or, as string theory suggests, perhaps black holes are fuzzballs, tangled balls of fundamental strings with no singularity at all. In this picture, there is no sharp event horizon, but a fuzzy, ill-defined surface that ingests matter and information. None of these ideas are yet proven. They are attempts to chart the territory that lies beyond the known limits of our physics. And the black hole is our guide. The questions it asks us are even more important than the answers we might find. It does not just ask, "What is over there?" It asks, "What is space-time? What is information? What is reality?" It is the ultimate confrontation between gravity and the quantum, the very large and the very small. When we look into these dark voids, we see not only the graves of stars but the source code of the universe itself, its most fundamental operating system. What was once a mathematical curiosity has become a gateway to the deepest mysteries of existence. With every new observation, with every new gravitational wave, we come a little closer to finding the key to unlock that door. But what awaits on the other side? For as long as we have known of the event horizon, we have been haunted by this question. General relativity tells us the journey ends at the singularity, a point of infinite density where matter is annihilated and our laws of physics crumble. But is that truly the end of the story? Is it possible that the universe's ultimate prison is also, paradoxically, an exit? This is where the mathematics of spacetime, the very blueprint of our reality, becomes stranger than any fiction, hinting at possibilities that challenge our very definition of place and time. Tunnels in spacetime. The same equations that described the one-way trap of a black hole also contained a glimmer of a different kind of passage. Albert Einstein and his colleague, Nathan Rosen, discovered that the geometry of a simple, non-spinning black hole mathematically required a sort of mirror image an anti-black hole connected to it. The link between them was a theoretical throat, a bridge through the fabric of spacetime itself. This became known as the Einstein-Rosen bridge, what we now call a wormhole. In theory, it is a cosmic shortcut, a tunnel connecting to vastly distant points in our own universe. Or perhaps connecting our universe to another entirely. The allure is undeniable. The ability to traverse the galaxy in an instant, to leap between dimensions. But physics is a harsh mistress. As our understanding deepened, this beautiful mathematical solution revealed its deadly flaws. The classic Einstein-Rosen bridge is now known to be dynamically unstable. The throat of the wormhole would pinch off and collapse into a singularity so quickly that not even a single photon, let alone a spaceship, would have time to pass through. Any traveler attempting the journey would be crushed out of existence in its violent implosion. To hold such a tunnel open would require something extraordinary, something that may not even exist, exotic matter. This is not just strange or rare matter, but a hypothetical substance with negative energy density. It would possess a kind of anti-gravity, pushing spacetime outward instead of pulling it in, propping the throat of the wormhole open against the immense force of its own collapse. While quantum mechanics allows for fleeting, microscopic pockets of negative energy to exist in a vacuum, we have no idea if it is possible to gather and stabilize enough of it to create a traversable passage. Even if one could be constructed, the intense radiation and tidal forces within would likely be lethal. The wormhole, for now, remains a tantalizing mathematical ghost, a reminder that within the rules of reality, there exist paths our current technology, and perhaps our very biology, can never tread. It shows us that spacetime is not just a stage, but a pliable, dynamic entity that can be folded, stretched, and perhaps even torn. The cosmic opposite, if the wormhole is a passage, another theoretical object is a destination with no entrance. For every mathematical solution describing matter falling inward to form a black hole, there exists a time-reversed version, matter exploding outward from a singularity. This is a white hole. It is the cosmic opposite of a black hole in every way. Where a black hole is a region from which nothing can escape, a white hole is a region into which nothing can enter. Light and matter can pour out of its event horizon, but the inward flow of spacetime is so overwhelmingly repulsive that no object from the outside can ever cross its boundary. Like wormholes, white holes are a perfectly valid mathematical solution to the equations of general relativity. Unlike black holes, however, we have never seen anything that looks remotely like one. There is a profound physical reason for this. The universe is governed by the second law of thermodynamics, the principle that entropy, or disorder, always tends to increase. The formation of a black hole collapsing a complex star into a simple point is a natural, entropy-increasing process. A white hole, which would spontaneously spew out organized matter and energy from a singularity, would be a flagrant violation of this fundamental law. It would be like watching a shattered glass spontaneously reassemble itself and leap back onto a table. There is simply no known physical process that could form one. Yet, the idea remains seductive. Some physicists have speculatively proposed that the greatest explosion of all, the Big Bang itself, shared characteristics with a white hole. A singular event from which all the matter and energy in our universe erupted forth. Could it be that what we perceive as the origin of our cosmos was, from some other perspective, the output of a gargantuan white hole? The connection is tenuous and highly speculative, but it serves as a powerful reminder that the most extreme objects in our universe touch upon the most fundamental questions of our own origin. A white hole is an answer to a question nature may not have asked, a perfect twin that was seemingly never born. The reign of darkness, the black hole era. Black holes are not just actors in the present cosmic drama. They are the inheritors of the universe's far future. To comprehend their ultimate significance, we must cast our minds forward, past the lifespan of our sun, past the last star in the sky, into an epoch of unimaginable cold and darkness. First comes the stelliferous era, our current age, filled with the light of stars. But stars are finite. In a few trillion years, the fuel for star formation will run out. The last red dwarfs will flicker and die, plunging the universe into the degenerate era. The cosmos will become a vast, silent graveyard populated only by the cold. Dead remnants of stars, white dwarfs, neutron stars, and black holes, all slowly radiating their remaining heat into the crushing cold of empty space. But this is just the beginning of the black hole's reign. Over timescales that dwarf 1 trillion years, galaxies themselves will dissolve as their stellar corpses are slowly ejected into intergalactic space. The universe will be dominated by a diffuse gas of elementary particles and a scattered population of black holes. This is the dawn of the black hole era. The only light, the only significant events will be the occasional merger of two wandering black holes, sending out one last, powerful gravitational wave into the silence. And even these giants will not last forever. According to Stephen Hawking's theory, they will evaporate. Through the steady, unimaginably slow leak of Hawking radiation, they will lose mass, particle by particle, over eons. A solar mass black hole will take 10 to the power of 67 years to evaporate. The supermassive black holes at the hearts of galaxies will persist for far longer. Perhaps 10 to the power of 100 years, a number so vast that if you were to write it out, the zeros would fill thousands of books. In the final moments of their long lives, they will shrink until they vanish in a final, weak flash of light and gamma rays. With the death of the last black hole, the universe enters its final stage, the dark era. A nearly perfect vacuum of cold, unbound particles, drifting ever further apart as the universe expands eternally. In this grand, cosmic narrative, black holes are the last, most enduring structures. They are the final act. The ultimate matryoshka doll, they may be the final act, but could they also have been the first? The idea of a singularity, the core of a black hole, has long been a sticking point for physics. What if, instead of being an end point of physics, a singularity is a new beginning? This has led to one of the most staggering and mind-bending ideas in all of cosmology: cosmological natural selection. This hypothesis proposes that every time a black hole forms in a universe, the singularity at its core gives rise to the big bang of a new baby universe, nestled within the parent but completely inaccessible to it. In this scenario, our own universe may have been born from the collapse of a star in a vast, older parent universe. Our Big Bang was the bounce of matter, creating a new realm of spacetime. This idea is profoundly attractive because it offers a potential explanation for why our universe has the physical constants it does, values that seem exquisitely fine-tuned for the existence of stars, galaxies, and life. The theory suggests that universes that are more effective at producing black holes by having constants that allow for the formation of massive stars will have more offspring. Over countless cosmic generations, universes fine-tuned for black hole production would become the most common. And since massive stars are also the source of the heavy elements necessary for life, it would be no surprise to find ourselves in a universe that is good at making both black holes and us. We can never test this. We can never see outside our own universe to look for our cosmic parent. It exists on the very edge of science, a place where physics bleeds into philosophy. But it is a powerful illustration of the central role black holes have come to play in our thinking. They are no longer mere celestial curiosities. They are the potential keys to understanding our past and our ultimate future. They are the place where the laws of nature are forged in the most extreme fires. A cosmic laboratory where spacetime itself reveals its deepest secrets. They are both a tomb and a womb, the engine of galactic evolution and the silent custodians of the universe's final twilight. They are the shadow that falls across the cosmos, and within that darkness, we search for light, for answers, and perhaps for the reflection of our own beginning. This search drives us to look ever closer at the veil of the event horizon, pushing not just our technology, but our very imagination to its absolute limits. While some theories cast our gaze outward to other potential universes, a quiet revolution in physics is exploring an equally radical idea: that we have fundamentally misunderstood what a black hole is. The paradoxes they present, the lost information, the firewall, the singular point of infinity might not be problems with the universe, but flaws in our description of it. They might be signposts pointing toward a new, deeper reality that lies just beneath the surface of what we can see. The holographic universe, one of the most profound and unsettling of these new ideas, is the holographic principle. Born from the study of black hole thermodynamics, it challenges our perception of space and reality in a fundamental way. It began with a simple but startling observation: the maximum amount of information that can be contained within a given volume of space. Its entropy is not proportional to the volume itself, but to the surface area of the boundary that encloses it. This is completely counterintuitive. Imagine a library. The amount of information, the number of books you can store, depends on the size of the room, its volume. But for a black hole, the information about everything that ever fell inside seems to be encoded, not throughout its three-dimensional interior, but on its two-dimensional event horizon. This led physicist Gerard T., Hooft and later Leonard Susskind to a radical hypothesis. What if this isn't just a strange property of black holes, but a fundamental principle of the entire universe? The holographic principle suggests that all the information describing our three-dimensional reality might be fully encoded on a distant, two-dimensional surface. In this view, the universe we experience with its depth, its texture, its sense of place is a projection, a hologram generated from information stored on a boundary at the edge of the cosmos. This is not to say that the universe is an illusion or a simulation. The chair you are sitting on is real, but the fundamental physics that describes it and its constituent particles may not ultimately play out in three spatial dimensions. Instead, it might be described by a simpler, flatter theory on a distant boundary, without gravity. The spacetime and gravity we experience would emerge from this flatter reality, much like a three-dimensional image emerges from a two-dimensional hologram. Black holes, in this context, become the ultimate theoretical test bed. They are small, self-contained universes whose holographic nature we can study, hoping to find clues about the grand cosmic hologram we may all be living in. The information paradox that so plagues black hole physics might be resolved if the information never truly enters the 3D volume, but is simply scrambled and stored on the 2D surface of the event horizon. This idea, while still highly theoretical, provides a powerful new lens through which to view the cosmos. It suggests a deep and mysterious connection between the laws of gravity and the principles of quantum mechanics, hinting that they may be two different languages describing the same underlying reality. The universe may be far stranger and perhaps more elegant than we ever imagined. The clues were there all along, not in the stars, but written on the surface of their shadows. The search for a quantum core, while some theories redefine the very fabric of spacetime. Others attempt to resolve the mystery by peering inside the black hole, looking for a way to dethrone the singularity. General relativity gives us this point of infinite density because it is a classical theory. It doesn't include the strange and probabilistic rules of quantum mechanics. At the immense energies and tiny scales near the center of a black hole, quantum effects must become dominant. A complete theory of quantum gravity would, most physicists believe, eliminate the singularity, replacing it with something even more exotic, yet physically plausible. What would that something be? One leading idea comes from loop quantum gravity, a theory that envisions spacetime not as a smooth sheet, but as a discrete, woven fabric made of finite, indivisible quantum loops. According to this theory, you can't just keep compressing matter indefinitely. There is a fundamental limit, a point where the quantized nature of spacetime itself pushes back, creating an immense outward pressure. This would prevent the formation of a singularity. Instead, matter falling into a black hole would be crushed down to an incredible but finite density, forming what is known as a Planck star. A Planck star would be an unimaginably tiny, hyperdense object hidden deep within the event horizon. But the story doesn't end there. The immense outward pressure would eventually cause this core to rebound in a phenomenal explosion. For an outside observer, because of the extreme time dilation near the black hole, this rebound would appear to happen over billions or trillions of years. In this view, a black hole is not a permanent prison, but a state of suspended animation. It is a long pause between an initial collapse and an eventual, very delayed explosion. The information that fell in isn't destroyed. It is held in this quantum state before being violently ejected. Some theorists have even speculated that this rebound could be what gives birth to a new baby universe. Connecting this idea back to the concept of cosmological natural selection. What we call a black hole could be, from the inside, a temporary gateway, a slow-motion bounce from one cosmic era to the next. These ideas are at the very frontier of human knowledge, blending observable astronomy with the most abstract and complex mathematics. They show us that black holes are more than just cosmic vacuum cleaners. They are the point of convergence, the place where our great theories of the universe relativity for the very large and quantum, mechanics for the very small meet and break down. By studying them, we are forcing these two theories into a conversation and in their contradictions. We hope to find the language of a deeper, more fundamental truth. A theory that can describe the entire cosmos from a single big bang to the deepest heart of a black hole as shadow.